गुड मॉर्निंग, नमस्कार, सुप्रभात। कैसे हैं आप सभी? In the last class we started to study about the semiconductors and we discussed intrinsic semiconductor at 0 Kelvin temperature. Let us begin to discuss these semiconductors at some other temperatures. Non-zero temperature पर इसको discuss करने का प्रयास करेंगे. Good morning everyone. So let us take 300 Kelvin. 300 Kelvin is considered to be room temperature. So let us talk about the behavior of this material at room temperature. So at case 2 at 300 Kelvin. Case 2. At नमस्कार, सुप्रभात, कैसे हैं आप सभी? At T is equal to 300 Kelvin. 300 Kelvin is room temperature. Now you see, these are the atoms. Silicon, all of them are having 4 electrons. So they make covalent bond with the neighboring atom. In the last class we discussed this. Same silicon crystal we are making. So all of them are making covalent bonds. These are covalent bonds. Covalent bonds. These. Let us suppose this is a semiconductor. This is valence band and this is conduction band. Suppose room temperature की thermal energy is sufficient to excite any electron from valence band to conduction band. Let us assume that the thermal energy at the room temperature is sufficient to bring an electron from conduction band from valence band to conduction band. As soon as electron goes to the conduction band, it becomes free electron, but a deficiency of electron is created in the valence band. जैसे ही इलेक्ट्रॉन कंडक्शन बैंड में जा रहा है, ये तो खुद फ्री इलेक्ट्रॉन बन जा रहा है, लेकिन वैलेंस बैंड में इलेक्ट्रॉन की एक कमी हो जा रही है. In the last case I told you कि at 0 Kelvin valence band is fully filled, but now one electron is going from the valence band, so valence band में एक state खाली हो जा रही है. One state is becoming empty in the valence band. This vacant electronic state या absence of electron in valence band is known as hole. Concept of hole is defined only for the semiconductors and that too in the valence band. So it means a hole is nothing but the vacancy in the valence band या absence of electron या deficiency of electron in the valence band. I will be talking about it later, but let us have a look here. क्या हो रहा होगा उस पे कोशिश करते हैं. Yes, it is the first slide, just we have started. So let us suppose this electron has become free electron. It has acquired sufficient thermal energy and it has become free electron. Once this electron is leaving this place, then a bond would be broken and a deficiency of electron will be created here. एक bond टूट जाएगा और इस जगह पर एक deficiency of electron क्रिएट हो जाएगी. यहाँ एक डिफिशियंसी ऑफ इलेक्ट्रॉन हो गई. ठीक. Now you see my dear friend, since this is the deficiency of electron, so this atom become unstable. Now this atom will try to bring stability. How the stability come? It needs one more electron and this bond need to be reformed. So it will try to snatch electron from any neighboring atom. Let us suppose this is snatching this electron and making this bond. So these two electron and hole will meet with each other and this bond will be reformed. Once this bond is reformed, these electron and holes meet each other, this bond is reformed, but this bond will be broken. This bond is broken and a hole is created at this place. क्या कह रहा हूं मैं कि ये इलेक्ट्रॉन चला जाने की वजह से ये एटम अनस्टेबल हो गया क्योंकि अब इसका ऑक्टेट कंप्लीट नहीं है। तो जब ये अनस्टेबल हुआ तो स्टेबिलिटी पाने के लिए नेबर के किसी इलेक्ट्रॉन को अपनी तरफ खींचेगा। लेट अस सपोज इस इलेक्ट्रॉन को इसने खींच लिया, ये इलेक्ट्रॉन यहां से यहां आया, ये दोनों इलेक्ट्रॉन और होल मिल करके रिकम्बाइन होकर के गायब हो जाएंगे, ठीक है। लेकिन इस जगह पर एक डिफिशियंसी ऑफ इलेक्ट्रॉन क्रिएट हो जाएगी और एक होल बन जाएगा। वैसे तो इलेक्ट्रॉन यहां से यहां आया, बट किसी एक्सटर्नल ऑब्जर्वर को लग सकता है कि एक होल यहां से यहां गया। ऑल्दो होल कैन नॉट मूव, इट इज जस्ट अ डिफिशियंसी ऑफ इलेक्ट्रॉन, still it seems that a hole is moving from this place to that place. Now you see, suppose this atom become unstable because of this hole, so it will try to snatch electron from the neighboring atom. So ये किसी neighboring atom से electron snatch करने की कोशिश करेगा. Once it is snatching electron from the neighboring atom, then a bond will be formed and here a covalent bond will be broken. Once this covalent bond is broken, a deficiency of electron is created here. This deficiency of electron is created, so this way it seems a hole is moving from this place to this place. You see, in the semiconductor there are two types of motion of charges. One, free electron moving into the conduction band, and another these valence electrons moving due to the vacant state in the valence band. This valence electron motion was not possible in the earlier case because in case 1 all the states were occupied, but here few states are becoming empty, so because of those empty states few electrons are moving into the valence band. We hardly consider this whether it is actually we need only the movement of electron, whether it is in the conduction band or in valence band, we hardly care for it. So मेरा कहना यह है कि हमारे लिए कोई फर्क नहीं पड़ता है कि इलेक्ट्रॉन कंडक्शन बैंड में मूव कर रहा है या वैलेंस बैंड में मूव कर रहा है। अगर इलेक्ट्रॉन मूव कर रहा तो इट वुड बी कंट्रीब्यूटिंग इनटू द करंट. So if electron is moving, whether it is in the conduction band or it is in the valence band, it will definitely be contributing into the current. So while calculating the conductivity, we have to consider the effect of both electrons. We have to consider the effect of free electron moving into the conduction band, as well as we have to consider the effect of valence electron moving into the valence band. But one thing, conductivity depends upon two factors. Conductivity is directly proportional to n mu n. So n is number of electron, but we have to see mobility of electron also. Whether mobility of electron is same in the conduction band and valence band or different. If mobility of electron is same in conduction and valence band both, then we need not to worry about it. We need to calculate overall number of electrons and multiply with mobility, we will get the conductivity. But suppose mobility of electron in conduction band and mobility of electron in valence band differ, then we have to consider the effect of these electrons separately. We have to calculate conductivity due to conduction electron and we have to calculate conductivity due to valence electron, and then we have to add this to get the overall conductivity. So let us try to investigate whether the mobility of electron in conduction band and valence band is same or different. For this purpose, let us do one experiment. Suppose there is a class, and in this class suppose there are 100 students. So out of like this way, you see, suppose there is a class and in that class there are 100 chairs. But out of these 100 chairs, only 20 chairs are occupied by the students, remaining 80 chairs are empty. Suppose, assume. Now I enter into the class and I start to say that please start moving. So since there are 80 empty chairs, only there are 20 students, so lots of empty space is available. So these students will be moving from one chair to another very frequently, and their mobility would be very high because of very low traffic level. Let us consider another case. There is a class and in that class there are 100 chairs. Out of these 100 chairs, let us suppose 80 are occupied by the students, only 20 chairs are empty. ऐसा मान लेते हैं कि 80 चेयर स्टूडेंट के द्वारा ऑक्युपाइड है और सिर्फ 20 चेयर्स खाली हैं. सो इफ ओनली 20 चेयर्स आर एम्प्टी. अब मैंने कहा कि दौड़ना स्टार्ट करिए. यस, मोशन विल हैपन बिकॉज 20 चेयर्स आर एम्प्टी. लोग इन खाली जगहों पर जाना चाहेंगे. बट देयर आर 80 persons, they are wanting to go for the 20 chairs. So traffic level would be very high, mobility would be very less. First case is related with the conduction band. In conduction band there are very few electrons. Lots of states are empty. So traffic level is very low. So conduction band electrons will be moving with very fast velocity. Whereas in valence band very less space is empty. Most of the states are occupied, very less states are empty. So valence band electrons would be moving very slow. So mobility of electron in conduction band will always be greater than the mobility of electron in valence band, because conduction band has very less electrons, lots of space is empty, so electrons will be moving with very fast speed. Whereas valence band electrons will have large traffic level, so they would be moving with slow speed. So we can say that mobility of electron, I can say that mobility of electron in conduction band is always greater than mobility of electron in valence band. Mobility of electron in conduction band is always greater than mobility of electron in valence band. पहली चीज. दूसरी चीज देखिए. Now since mobility of electron in conduction band and mobility of electron in valence band both are different, so we need to consider these electrons separately. We cannot consider them as same electron, because if mobility is high, conductivity will be high because of that electron, and if mobility is low, conductivity will be low. So conduction band electrons means this free electron will be contributing more current than this valence electron which is moving into the valence band. So we have to consider these two electrons separately, but there may be confusion. So in order to avoid this confusion, one assumption was done. What was that assumption? Assumption was done कि electron means by default still we would be talking about free electrons, that is in the conduction band. But in order to consider the motion of these valence electron, let us consider hole as a particle. Although hole is not a particle, but let us assume that hole as a particle for all practical purposes to consider the motion of electrons in the valence band. Once we consider hole as a particle, then we need to forget that any electron is moving into the valence band. Then we can say that ki holes are moving into the valence band. So we are assuming hole as a particle moving into the valence band. Now we will have two kind of particle in the semiconductor, one free electrons moving into the conduction band and another holes moving into the valence band. One moment, if you are considering hole as a particle, you must have to give charge to it. So how much charge would be decided for hole? You see, when hole is created, one electron is leaving this atom. Earlier this atom was neutral, but when the electron is leaving, a positive charge will come onto the atom. So hole is given a positive charge. Hole is a positively charged particle. And how much charge? जितना चार्ज निकल करके गया है, तो कितना निकल के गया है? एक इलेक्ट्रॉन के मैग्नीट्यूड के बराबर. So it means hole is having positive charge equal in magnitude to the electron charge. So this way we will consider hole as a particle which is moving into the valence band having equal charge in magnitude to the electron charge but opposite in sign. It is positive particle. Now both electrons and holes will contribute into the current in a semiconductor. Electrons will move into the conduction band and holes will move into the valence band. Forget about the valence electron, क्योंकि valence electrons को ही consider करने के लिए आपने hole को particle माना है. अब अगर आपसे कोई पूछे कि होल और इलेक्ट्रॉन में मोबिलिटी किसकी ज्यादा है, सो मोबिलिटी ऑफ इलेक्ट्रॉन इज ऑलवेज ग्रेटर देन द मोबिलिटी ऑफ होल। मोबिलिटी ऑफ इलेक्ट्रॉन का मतलब कौन सा, फ्री इलेक्ट्रॉन, और होल का मतलब कौन सा, वैलेंस इलेक्ट्रॉन। और मैं पहले ही लिख रहा हूं कि कंडक्शन बैंड में ट्रैफिक लेवल कम है, इसलिए कंडक्शन बैंड इलेक्ट्रॉन्स आर फास्टर एज कंपैरिजन टू द वैलेंस बैंड इलेक्ट्रॉन। इट मींस मोबिलिटी ऑफ इलेक्ट्रॉन इन कंडक्शन बैंड इज ग्रेटर देन मोबिलिटी ऑफ इलेक्ट्रॉन इन वैलेंस बैंड। बट मोबिलिटी इलेक्ट्रॉन जो वैलेंस बैंड में, उन्हें हम लोग क्या नाम दे रहे हैं, होल। ठीक है, सो इट मींस मोबिलिटी ऑफ इलेक्ट्रॉन इज ऑलवेज ग्रेटर देन मोबिलिटी ऑफ whole. Whole means valence electron. So we can write it mobility of free electron. Free electron means electrons which are in conduction band. Mobility of free electron is always greater than mobility of holes. Mobility of free electron is always greater than mobility of holes. Mobility of free electrons is always greater than mobility of holes. You can also write like this. Acha, one moment. So when these electrons and holes are created, when we are increasing temperature, so they are basically thermally generated charge carriers. Because at 0 Kelvin there was no free electron, there was no hole. When hole and free electron is created when we are increasing temperature, so they are due to temperature, it means they are due to thermal effects. So hence it means they are thermally generated charge carriers. So these electron hole pairs are generated due to increase in temperature, so they are thermally generated charge carriers. First thing. Second thing, आप देखिए, whenever one electron is moving up, immediately one hole is created, another electron is moving up, another hole is created. So these electrons and holes are created in pairs, so they are equal in number. So at any temperature, number of electrons in conduction band is equal to the number of holes in valence band. So we can write at any temperature, किसी भी टेम्परेचर पर n is equal to p. N is number of free electrons per unit volume, P is number of holes per unit volume. This must be equal to Ni, I for intrinsic semiconductor. Ni is known as intrinsic carrier concentration. This Ni is known as intrinsic carrier या charge carrier, intrinsic charge carrier concentration. It is very important parameter. Sometimes students get confused कि if there are 10 electrons and 10 holes, then Ni की value 20 होगी. No, it's not sum. It is basically equal to number of electron hole pairs. How much pairs are there, उसे हम लोग intrinsic charge carrier concentration कह रहे हैं. So you can define it. It is defined as number of electron hole pairs that is EHPs per unit volume in an intrinsic semiconductor. Number of electron hole pairs per unit volume in an intrinsic semiconductors. This Ni is a strong function of temperature because at the 0 Kelvin there was no electron hole pair. But you are increasing the temperature, then electrons are going up and electron hole pair is creating. So as you keep on increasing temperature, this value will keep on increasing. So this Ni is related with temperature and it is given as Ni square is A naught T cube e to the power minus Eg naught Ni square is A naught T cube e to the power minus Eg naught upon Kt. Ni is intrinsic carrier concentration, intrinsic carrier concentration at T Kelvin. A naught is material constant, material constant. Eg naught is energy gap at 0 Kelvin, energy gap at 0 Kelvin. K is Boltzmann constant, Boltzmann's constant. It is Boltzmann constant. ठीक, K is Boltzmann constant. Either it is non-linear function of temperature. It is not linearly varying. It is non-linear function of temperature. One more. Let us suppose we are at constant temperature and we compare two materials. So the material which have narrow band gap, more number of electrons would be moving to the conduction band, and the material which has wide band gap, less number of electrons would be moving. So materials having narrow band gap will have higher value of Ni as comparison to the materials having wide band gap. So basically, if you see intrinsic carrier concentration Ni in germanium is greater than Ni in silicon because energy band gap Eg of germanium is less than Eg of silicon. ठीक है. So this is all about the case 2. आप इतना पहले लिख लें तो मुझे यहाँ कुछ बातें लिखाना है, आपको लिखा दूंगा. First you write these things. होल कुछ है ही नहीं, इलेक्ट्रॉन जो मूव कर रहा बैलेंस बैंड में उसी को समझने के लिए हम लोगों ने होल मान लिया है. बाकी होल इज अ वैकेंट स्टेट, जहां पर बैलेंस बैंड में इलेक्ट्रॉन था वो हट गया तो उसे हमने होल कह दिया. आंखों से तो हम इलेक्ट्रॉन भी नहीं देख सकते, होल की तो बात ही छोड़िए. Naked eyes are not able to see this. हाँ, फ्री इलेक्ट्रॉन बहुत ज्यादा होंगे, एक से मैं समझा रहा हूं अर्पित. इट्स नॉट ओनली वन इलेक्ट्रॉन होगा. रूम टेम्परेचर पर 10 टू द पावर 10 की रेंज में होते हैं पर यूनिट वॉल्यूम. Yes, when valence electrons are becoming free, then hole is created. When it will become free? When it will go to the conduction band, then only it will become free. Management has told me to increase your class timing. So tomorrow onwards they said me to take the class from 8:30 AM onwards. So कल से क्लास 8:30 बजे से होगी, सुबह 8:30 से 12. They told me to announce this schedule. Tomorrow onwards the class would be from 8:30 to 12. Done? एक पॉइंट लिख लें. At room temperature, few of the electrons acquire sufficient energy and they move into the conduction band. When an electron moves to conduction band, a deficiency of electron is created in valence band, which is known as hole. Which is known as hole. Although hole is not a particle, it is just a deficiency of electron. In valence band. But for all practical purposes, hole is assumed as a particle having positive charge equal in magnitude to electron charge, having positive charge equal in magnitude to electron charge. Although hole is not a particle, it is just a deficiency of electron in valence band, but for all practical purposes, hole is assumed as a particle having positive charge equal in magnitude to electron charge. In semiconductors, both electrons and holes contribute in electrical conductivity, contribute in electrical conductivity, holes move in valence band and electrons move in conduction band. Electrons move in conduction band. Move in conduction band. Please note down this theory. It will help you to understand the things a bit more. Whatever I told, I have written same things. लगभग ये पूरा वीक लगेगा. आज संडे है, सैटरडे तक या संडे तक जाएगी सब्जेक्ट, संडे तक जाएगी लगभग. समवन इज आस्किंग कितना समय लगेगा, तो अप्रॉक्सीमेटली अप टू सैटरडे या संडे. बेटा पिछले 1 घंटे से निष्ठा एक्सप्लेन किया है, तो अब 1 घंटा रिपीट कर पाना पॉसिबल नहीं है सेम चीज़ के लिए. मैं सलाह दूंगा कि जब भी आपको मौका मिलेगा बाद में वीडियो से देख लीजिएगा. नेक्स्ट, conductivity of intrinsic semiconductor. Conductivity of intrinsic semiconductor. For intrinsic semiconductor, I represent it by sigma I. हम लोग इसे सिग्मा आई से रिप्रेजेंट करते हैं. ठीक है. आई फॉर इंट्रिंसिक, सिग्मा मीन्स कंडक्टिविटी. फॉर मेटल्स वी राइट फॉर अ सेमीकंडक्टर, लिख लेते हैं इन जनरल फॉर अ सेमीकंडक्टर. इन सेमीकंडक्टर बोथ इलेक्ट्रॉन्स एंड होल्स कंट्रीब्यूट. सो कंडक्टिविटी ड्यू टू इलेक्ट्रॉन्स, सिग्मा इज इक्वल टू ड्यू टू इलेक्ट्रॉन्स इज n q mu n. What will be due to holes? In place of n, there would be holes p, number of holes per unit volume. Magnitude of charge is same on both, and mu p is mobility of hole. So mu n is mobility of electron. n और p मैं पहले ही बता चुका हूं पिछली हेडिंग में ही. mu p is mobility of hole. Q is magnitude of electron charge, that is 1.6 into 10 raised power minus 19. That is same on both. Add कर दीजिए इन दोनों को. This is the general expression to calculate the electrical conductivity of a semiconductor. Both are contributing here. Let us suppose n is equal to p is equal to ni. If n is equal to p is equal to ni, then sigma I is equal to ni q mu n plus ni q mu p. So sigma I is ni q कॉमन ले लीजिए, mu n plus mu p, this is 1 upon rho I. दिस इज सिग्मा आई. ठीक है जी, ये वैल्यू हो जाएगी सिग्मा आई की. रो इज रेजिस्टिविटी. मित्रों जो ये मोबिलिटी है मेटल्स में, तो हमने क्या लिखा था कि म्यू इज डायरेक्टली प्रोपोर्शनल टू टाउ एंड टाउ इज इनवर्सली प्रोपोर्शनल टू रूट ऑफ टी. रूट ऑफ टी का मतलब टी टू द पावर -1/2. लेकिन सेमीकंडक्टर्स का क्रिस्टल स्ट्रक्चर डिफरेंट होता है, तो उसमें जो मोबिलिटी होती है वो -1/2 नहीं बल्कि -3/2 से वेरी करती है. सो फॉर सेमी कंडक्टर्स, mu n is directly proportional to T to the power -3/2 with respect to temperature, and similarly mu p is also varies in the same fashion, T to the power -3/2. हम लोग अगर प्रोपोर्शनैलिटी हटाएं तो एक प्रोपोर्शनैलिटी कांस्टेंट आ जाएगा. मैं म्यू एन नॉट मान लेता हूं, इट इज अ कांस्टेंट, प्रोपोर्शनैलिटी कांस्टेंट, T to the power -3/2, and mu p is equal to mu p naught T to the power -3/2. Intrinsic concentration, I told you, Ni square is equal to A naught T to the power e to the power minus Eg naught upon Kt. So from this, Ni is equal to root of A naught T to the power 3/2 e to the power minus Eg naught upon 2Kt. So let us put these values in this expression. If I put these values here, sigma I is equal to Ni root A naught T to the power 3/2 e to the power minus Eg naught 2Kt into mu n naught T to the power -3/2 plus mu p naught T to the power -3/2 into Q. Q भी है, Q लिखना भूल गया था. दिस इज द कंडक्टिविटी. तो जितने भी हमारे पास फैक्टर्स हैं इनको एक साथ कर देते हैं. सिग्मा आई इज रूट ए नॉट क्यू म्यू एन नॉट प्लस म्यू पी नॉट T to the power 3/2 minus T to the power 3/2 minus Eg naught 2Kt. ठीक. अब एक चीज देखिए, ये पूरा टर्म तो क्या है, एक कांस्टेंट है. ये सारी वैल्यू क्या है, कांस्टेंट है. ये T to the power 0 हो जाएगा, T to the power 0 that is equal to 1. So बचा क्या, this whole value, let us suppose a constant value, let us assume C1 मान लेता हूं. So sigma I is equal to C1 e to the power minus Eg naught minus Eg naught upon 2Kt, right? So we can write it something like this. Sigma I is C1 upon e to the power Eg naught 2Kt. आप एक चीज देखिए, यदि आप टेम्परेचर बढ़ाओगे तो ये वैल्यू बढ़ेगी, ये ओवरऑल कम होगा, ओवरऑल वैल्यू सिग्मा की बढ़ेगी और रेजिस्टिविटी कम होगी. इट इज अपोजिट टू द मेटल्स. इन मेटल्स विद इंक्रीज इन टेम्परेचर कंडक्टिविटी वाज डिक्रीजिंग, because in metals with increase in temperature mobility decreases and number of carriers remain constant, so overall conductivity decreases. Here with increase in temperature mobility decreases. This expression says that mobility decreases, but intrinsic carrier concentration increases heavily. So this increase in carrier concentration dominates over decrease in mobility and overall conductivity increases. So we can say that in an intrinsic semiconductor, with increase in temperature, conductivity increases because increase in carrier concentration, increase in carrier concentration dominates over decrease in mobility, dominates over decrease in mobility. ठीक, please note down this. We moved from here, conductivity of intrinsic semiconductor. Sagar Manucha is asking, sir, will you be taking material science for electrical also at the same time? Abhi to nahi shayad, they would be making schedule later. So when the schedule will be coming to me, I would be taking it. But I don't think they are planning in continuity. If they will plan, management people will plan in continuity, I will do it in continuity. If they are not planning in continuity, then let's see whenever they give the syllabus. No, Ruchi Agrawal is asking कि सर GS की कट ऑफ कॉमन होती है ऑल ब्रांच की? नहीं बेटा, सेपरेट होती है ब्रांच टू ब्रांच, बिकॉज योर कंपटीशन इज विद इन योर ब्रांच, सो कॉमन कट ऑफ का कोई लॉजिक ही नहीं उठता है. सिविल वालों का सिविल के साथ, मैकेनिकल का मैकेनिकल के साथ, ईसी का ईसी के साथ, इलेक्ट्रिकल का इलेक्ट्रिकल के साथ. सो कॉम्पिटिशन इज नॉट इंटर ब्रांचेस, इट इज विद इन ब्रांचेस. मैं फिर से रिपीट कर रहा हूँ, टुमारो ऑनवर्ड्स द क्लास वुड बी फ्रॉम 8:30 AM ऑनवर्ड्स. सुबह 8:30 बजे से और 12 बजे तक क्लास रहेगी. थोड़ा सा सो करके जागने में आपको असुविधा होगी, जल्दी जाग जाइएगा. दे टोल्ड मी टू इंक्रीज द क्लास आवर्स बाय हाफ एन आवर. सो आफ्टरनून में तो पॉसिबल नहीं है, लेकिन मॉर्निंग में 8:30 से क्लास होगी. Someone said to show the previous slide. Just quickly see the previous slide. We started from here today. This is the first slide. Quickly they see it. Then we did this. Then we did this. Then we are doing this, we are doing this. This and this. The biggest problem with the intrinsic semiconductor is all other things are constant with except temperature. So conductivity of intrinsic semiconductor can be increased only by increasing temperature. There is no possibility of other than increasing temperature. Abhishek Nagdeshi is saying that, sir, Hyderabad mein thand nahi hai, weather is very comfortable. Yes, Hyderabad weather is very lovely. This year I was approximately around 20 days in Hyderabad, and during rainy season I was there, and it was very lovely weather. And I was having a class of only 4 hours, I think. So in the evening, 5 to 9, we were having class. So remaining time I wandered here and there in the city. That is a very lovely city, beautiful city. So, and weather is also very good. In Delhi, weather is very harsh. Delhi I don't like in terms of weathers. What I told you, ki the conductivity of intrinsic semiconductor is function of temperature only. It varies only with the temperature. There is no other parameter which can control the conductivity, because Eg naught is energy gap at 0 Kelvin. So for a particular material its value is fixed. So you can change the value of only temperature. So by increasing temperature, the conductivity of intrinsic semiconductor can be increased, and if you do not increase the temperature, conductivity cannot be increased. Now let us see how much is the conductivity of this material at room temperature. For our surprise, the most useful material, silicon, is having 1 upon ohm centimeter inverse, which is approximately 0 at room temperature. This I am saying at room temperature. At room temperature, the conductivity of intrinsic silicon is 1 by 2,30,000, which is almost equal to the 0. It means this material is not useful for room temperature applications, because at room temperature you will get negligible conductivity. It is just like insulator. So we will not prefer this semiconductor at the room temperature. Where we will be preferring it? Where we are increasing the temperature for those applications, or we are shining light, because when we will put light, light will give energy to the electrons, electron hole pairs will be created, Ni value will increase, conductivity will increase. So we can use it in those applications where we are shining light or we are increasing the temperature. In other applications at the room temperature it is useless. In other applications at the room temperature it is useless because of its negligible amount of conductivity. So what we will do? We will go for some other material. Why? Because most of the electronic devices we have to use at the room temperature. The camera which is recording my video, that is a semiconductor device and it is kept at the room temperature. TV in your house, that is an electronic device, that is at the room temperature. The laptop in which you are watching to me, that is at the room temperature, electronic device, and that is at the room temperature. So most of the electronic devices we have to operate at the room temperature. ऐसा तो है नहीं कि आप लैपटॉप ऑन करके और पहले उसके नीचे आग लगा करके एंड देन यू विल बी वेटिंग कि इसका टेम्परेचर इंक्रीज हो जाए, देन सर हमें दिखाई देंगे. That's not like the case. So it means we have to operate these all devices at the room temperature. So this material should have better conductivity at the room temperature. But दुख की बात है, इस मटेरियल की कंडक्टिविटी रूम टेम्परेचर पर अच्छी नहीं है. दिस मटेरियल इज नॉट हैविंग गुड कंडक्टिविटी एट द रूम टेम्परेचर. So intrinsic semiconductors are less useful. Now we are going towards another semiconductor. That semiconductor is known as extrinsic semiconductor, and most of the electronic devices are made of extrinsic semiconductor. Why? We take an intrinsic semiconductor and we add a small amount of impurity in the intrinsic semiconductor. When we add a small amount of impurity, so the resulting semiconductor is impure semiconductor, and that impure semiconductor has very high conductivity than the pure semiconductor, and even at room temperature, at constant temperature, that may give us very high electrical conductivity. That material we would be using to make the electronic devices. किसी को लगेगा कि यार कल तो सर ने कहा था कि जब हम impurity ऐड करेंगे तो इलेक्ट्रॉन स्कैटर होगा and mobility will decrease. Yes, even today I am saying that when we are adding impurity into the pure semiconductor, that will scatter the electron, mobility will decrease. But conductivity is not function of mobility only, it is the function of n and mu n. So first of all, try to select the impurity atom which will scatter electron very less. That will be possible if the semiconductor atom and impurity atom are almost of the same size. So scattering would be minimum. Then decrease in mobility would be minimum, and increase the carrier concentration by using this mobility, and this way your conductivity will increase. So this is the idea behind the doping. Doping means adding impurity. So to make the extrinsic semiconductor, the idea is select an impurity atom which is almost of the same size of the silicon atom, so that scattering of electron will become minimum. For electron, the crystal structure will remain almost same as it was in the pure semiconductor. So scattering will be minimum, but increase the carrier concentration, and this way conductivity will increase. That is the idea. So now we need to select such an impurity which is almost of the same size as the silicon atoms. So silicon is in the fourth group. Silicon is in fourth group. So almost same size atoms are either in third group or in fifth group. Almost same size atoms are either in third group or in fifth group. So we can add impurity of either third group elements or fifth group elements. Apart from that, nothing can be added as an impurity. If you add second group elements, they are very large and scattering would be very high, mobility will decrease so much that conductivity will start decreasing, purpose will defeated. We are not going to add. If you add 6th or 7th group elements, they are so small, so when they will enter, so they will try to enter into the interstitial stages and they will try to scatter the electron. So we need to select almost same size impurity, and same size impurity, almost, not exactly, almost same size impurity can be got by the immediate neighbors, either 3rd groups or 5th groups. So we will have 2 types of impurities, and this way we will be having 2 types of extrinsic semiconductor. One because of 3rd group, that is known as p type semiconductor, another because of 5th group, that is known as n type semiconductor. So next we are going to study these n and p type semiconductor. Next heading is extrinsic semiconductor. Next heading is extrinsic semiconductor. Abhishek, formula you need not to remember. Actually, you need to remember the conclusion. That's why I am putting in box those formulas. With increase in temperature, how the conductivity is varying, how the resistivity is varying, whether it is increasing or decreasing. That kind of conclusion should be in your mind, because they would be asking the conceptual questions and theoretical questions, not the formula based. लिखेंगे at room temperature, intrinsic semiconductor has very small conductivity, hence it is less useful. Most of the electronic devices are made of a semiconductor, in which a small amount of impurity has been added. The process of deliberately adding impurity to a pure semiconductor deliberately adding to a pure semiconductor is known as doping. The process of deliberately adding impurity to a pure semiconductor is known as doping. Such doped semiconductors are known as extrinsic semiconductor, or impure semiconductors, or impure semiconductors, impure semiconductors. Conductivity of impure semiconductor is greater than pure semiconductor, conductivity of impure semiconductor is greater than pure semiconductor. Please. Do it quickly. किसी ने फाइनल पार्ट ऑफ इंट्रिंसिक कहा था, क्विकली डू इट. Let's go. So now let us try to study N and P type semiconductors. Let's try to study N and P type semiconductors, because extrinsic semiconductors are two types. So first one is N type semiconductor. N type. First one is N type. We take an intrinsic semiconductor. Let us suppose this is our intrinsic semiconductor. So each atom has 4 electrons. Each of them are having 4 electrons. हर एक एटम के पास 4 इलेक्ट्रॉन है. Now we are wanting to dope it, wanting to dope it. Let us suppose this is the band diagram. Since it is a solid, so solid has band. So it is valence band EV and it is conduction band EC. If we are doing doping, before doping it is kept at some temperature, because doping would be done at the some temperature. So before doping it is intrinsic semiconductor, and in the intrinsic semiconductor there must be some electrons and there must be some holes. So before doping, whatever are electrons and holes, they are equal in number. That is represented as Ni. This is due to temperature. Although at room temperature this number is 1.5 into 10 to the power 10 per centimeter cube, very large. इतने electrons हैं और इतने hole हैं. But to explain, I am taking it as 100 and 100. Just for explanation purpose. It is not any practical data. Now I am doping it. To make the N-type semiconductor, we will add fifth group impurities. Fifth group impurities are added. Fifth group has 5 valence electrons, so they are known as pentavalent impurity. They are known as pentavalent impurity. Some important pentavalent impurities are phosphorus, arsenic, antimony, etc. Very few atoms of these impurities are added. Out of 10 to the power 7 silicon atoms, we generally add 1 phosphorus atom. So very small amount of impurity is added. Let us suppose we are adding a phosphorus. So phosphorus has 5 valence electrons. Since it is an atom of phosphorus, so for an atom, energy is represented in terms of discrete energy level. So these 5 electrons would be at the outer orbit energy level of phosphorus. You can find out the outer orbit energy level of phosphorus, that is ED. So we have two graphs, one for phosphorus and one for semiconductor. Let us superimpose them. यानी एक ही पेपर पर दोनों ग्राफ को बना देते हैं या बना करके एक दूसरे के ऊपर सुपर इम्पोज कर देते हैं. So when we superimpose them, we find out ED is slightly below EC. ED is outer orbit energy level of phosphorus. It is roughly around 0.05 electron volt, the difference between these two, if doping is done in silicon. Very small gap. Now suppose I replace this atom when we do the doping. So when this silicon atom is removed, these 4 bonds will be broken and a phosphorus will come here into the picture. एक phosphorus आ जाएगा. This phosphorus will have 4 electrons and 1 extra electron. So we would be having this electron bond, this bond and this bond. 4 bonds would be formed, but 1 electron will remain still extra. 4 bonds are reformed, crystal structure will become same as it was earlier, but this phosphorus is having 1 more electron. Where is this electron? Here this electron is. So now phosphorus does not need this electron, so phosphorus will donate this extra electron to the semiconductor. So this electron will move to the conduction band. It means what? Each phosphorus atom is donating 1 free electron to the semiconductor. So जितने भी phosphorus atom आप डालोगे उतने extra electron create हो जाएंगे semiconductor में. Is there any hole created? No. holes are not created. Hole would have been created if electron is going from valence band to conduction band, but electron is not going from valence band. Electron is going from phosphorus to the conduction band. So this way holes are not created. Overall semiconductor will remain neutral because one extra electron is created due to the phosphorus, then phosphorus will acquire positive charge. So every phosphorus atom will become a positive ion. These phosphorus atoms are donating electron, so they are known as donor ions. Now you see, let us suppose we add 10 phosphorus atom. मान लेते हैं कि we are adding 10 phosphorus atom. So each are giving 1 electron, so we will have 110 electrons and 100 holes. Now you see, earlier hole and electron were same. Now electrons are large in number and holes are less in number. Since electrons are large in number, so it is known as n-type semiconductor because electron has negative charge. Electron become majority charge carrier and holes become minority charge carrier. And fifth group impurity is known as donor type impurity because they are donating electron. So these are donor type impurity, and electrons are majority charge carriers. Electrons are majority charge carriers, Holes are minority charge carriers. This is overall N and P type semiconductor. Sorry, it is N type. P type के लिए आगे बात करेंगे. Please note down it. Do it quickly. But Akhilesh, since it is at the some temperature, you are doing doping, so obviously the process would be at room temperature at some temperature, and that thermal energy is sufficient to donate electron from phosphorus to the semiconductor because you need only 0.05 electron volt. That is very small energy to move an electron from ED to EC, right? So this way any temperature which is greater than 0 Kelvin, that would be sufficient, and 0 Kelvin is not practically achievable temperature, so we need not to worry about that because 0 Kelvin पर तो doping होना possible ही नहीं है. 0 Kelvin हम कभी achieve ही नहीं कर सकते हैं. Doping तो किसी practical semiconductor में करोगे, and practically 0 Kelvin is not achievable temperature. जीरो केल्विन पर ओंकार ये डोनेट नहीं कर सकता, बट 0 केल्विन पर डोपिंग कर पाना संभव है. 0 केल्विन इज नॉट अ प्रैक्टिकल टेम्परेचर, दैट इज अ थ्योरेटिकल कंसेप्ट. अभिषेक कह रहे हैं कि सर इफ दिस सेमीकंडक्टर वाज अ स्पोर्ट पर्सन देन इट वुड बीन गॉट बैंड फॉर 4 years फॉर डोपिंग। हाँ, वो भी सेम कंसेप्ट है कि स्पोर्ट पर्सन भी डोपिंग इसीलिए करते हैं ताकि वो अपनी क्षमता बढ़ा सकें। फास्फोरस के लिए रोहन बैलेंस बैंड नहीं बनेगा, बैलेंस ऑर्बिट, बिकॉज वी आर टेकिंग वेरी फ्यू इलेक्ट्रॉन्स of very few atoms of phosphorus. So for the atoms we represent energy level and for the solid we represent energy band. इसीलिए मैंने दोनों को अलग अलग बनाया है। रोहन, B निष्ठा B add roughly around, it's not always, one donor atom, donor मतलब phosphorus, in 10 to the power 7 silicon atoms. One donor atom in 10 to the power 7 silicon atoms. आई सिमिलरली पी टाइप, वहां पर इंप्योरिटी थर्ड ग्रुप की हो जाएगी। पी टाइप again we would be taking an intrinsic semiconductor, let us suppose silicon, 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 this is the silicon. It is the semiconductor. Here conduction band, here valence band. So intrinsic semiconductor. Now suppose third group impurities are added. Third group impurities are added. Third group impurities are added. Third group has 3 valence electrons, so they are known as trivalent impurities. Some important trivalent impurities are boron, aluminum, gallium, indium, etc. Let us suppose we are adding a boron. We are adding a boron. Boron has 3 electrons. 3 electrons. These 3 electrons are in the valence orbit of boron. ध्यान रहे किसी भी तरह से क्रिस्टल स्ट्रक्चर चेंज नहीं होना है, क्रिस्टल स्ट्रक्चर सेम रहना है, ठीक। So this atom is having 4 bonds in this crystal structure. Now we are removing this and in place of this we are bringing a boron atom. In fact we are doping it. This bond will be broken and a boron will come into picture. This boron is having 3 electrons. So it will bond with neighboring 3 atoms. 3 bond will be formed, but 4th is incomplete. Crystal structure will change. This boron needs 1 more electron to retain the same crystal structure so that चारों bond बन सके. But you see, my dear friend, it has only 3 electrons. If you plot this same energy level overlapping, so this EA will come very close to the valence band. This is 0.05 इलेक्ट्रॉन वोल्ट अप्रॉक्सीमेटली, फिर से सिलिकॉन में लगभग इतना। अब ये गैप बहुत नैरो है, तो किसी भी टेम्परेचर पर स्लाइटली ग्रेटर देन 0 केल्विन टेम्परेचर होगा, सो सम इलेक्ट्रॉन विल बी मूविंग फ्रॉम valence band to EA, and this way a hole is created in the valence band. Basically what happened, one electron moves from here to here, and because of this movement this covalent bond is reformed and a deficiency of electron is created here, so a hole is created here. Since this impurity is accepting electron, so इस पे एक नेगेटिव चार्ज आ जाएगा, ये नेगेटिव चार्ज और होल एक दूसरे को बैलेंस कर देंगे. There is no extra electron, extra hole has been created, so number of holes will increase, and that's why it is p-type semiconductor. Since this type of impurity is accepting electron from semiconductor, so third group impurities are known as acceptor type impurity. So this is third group impurity, this is known as acceptor type impurity. Acceptor type impurity, acceptor type impurity. Holes are majority charge carriers, majority charge carriers. Electrons are minority charge carriers, electrons are minority charge carriers, minority charge carriers, electrons are minority charge carriers. Holes are majority charge carriers, electrons are minority charge carriers. Please note down it. Done? Which one you will prefer, n-type or p-type? Obviously n-type will be preferred, because in n-type majority carriers are electrons, holes are negligible, and in p-type majority carriers are holes, electrons are measurable. So in p-type mainly conduction is because of holes, and in n-type mainly conduction is because of electrons. And in the last heading I told you कि mobility of electron is always greater than mobility of hole. It means for same amount of doping, n-type semiconductor will give higher conductivity than the p-type semiconductor, and this is the reason n-type semiconductor based devices will be preferred over p-type semiconductor based devices. So let's talk about conductivity of these materials. Conductivity of n and p type semiconductors. आज मुझे ऐसे लग रहा बहुत देर से पढ़ा रहे हैं, अभी कुछ खत्म ही नहीं हुआ. टायर्ड, सुबह सुबह ही थकान लग गई है. वेरी टायर्ड इन द अर्ली मॉर्निंग इटसेल्फ. रात में नींद पूरी नहीं हुई. Was reading few things. चाय पी लें तो अगली हेडिंग करते हैं. आज थोड़ा आईएएस कम दिख रहे हैं. I mean, some less people are attending classes. Challenge. Conductivity of extrinsic semiconductor. Conductivity of extrinsic semiconductor. For a semiconductor, sigma is equal to NQ mu n plus PQ mu p. For n-type semiconductor, electrons are majority carriers, so n is greater than p. और अगर n p से बड़ा है तो this portion can be neglected. Sigma n is equal to nq mu n. Sigma is NQ mu n. For p-type semiconductor, P is greater than n. P is greater than n. So if P is greater than n, this can be neglected. So sigma is approximately PQ mu P. And this is the reason I said that n-type semiconductor devices will be preferred over p-type semiconductor, because for same carrier this will provide more conductivity. Mu n is greater than mu p, so conductivity of n-type will be greater than p-type. So you can write it. N-type semiconductor based devices will be preferred over p-type semiconductor based devices, because mobility of electron is always greater than mobility of hole. Mobility of electron is always greater than mobility of hole. You please do it. Tushar Agrawal, yes, you found it correctly. एक्चुअली आई हैव वेरी इंटरेस्ट इन फिजिक्स है, हालांकि मेटाफिजिक्स नहीं पढ़ रहा था कल। एक सिविल सर्विसेज में एक टॉपिक होता है साइंस एंड टेक, तो उसके कुछ टॉपिक्स पढ़ रहा था। एक्चुअली आफ्टर फ्यू डेज वेरी सून द रिजल्ट ऑफ सिविल सर्विसेज मेंस वुड बी अनाउंस्ड, So you may be knowing that कि MADG has a sister organization Next IAS. So their students prepare for civil services examination. So although I am the integral part of MADG group, I take mainly the technical subjects here, but I have few classes at Next IAS also, and particularly for interview guidance I have a small role over there. So I was just brushing up my notes and knowledge, because in civil services things are related with current affairs, they are not static like this. So पूरे साल भर में क्या साइंस एंड टेक में देश में हो रहा है नहीं हो रहा वो समराइज करना पड़ता है, so that I can guide them in interview in the proper manner. So I thought that ki when the result would be announced, then I would be having very little time to revise all those things, पूरे साल भर की घटनाएं and all those things. So this would be difficult. So let's keep on revising before the result is announced. So was studying those things only. Conductivity of extrinsic semiconductor. अरे मनोज, मुंबई का मौसम तो हमेशा अच्छा रहता है, मुंबई के मौसम में ऐसा क्या हो गया? द वेरी लवली वेदर एट मुंबई ऑलवेज. आना है यार इस बार मुंबई, काफ़ी दिनों से प्लान बन रहा है. देर आर सो मेनी कॉलेजेस एंड फॉर सम ऑफ द कॉलेजेस आई हैव accepted invitation but not confirmed. So let's see, this year we'll try to deliver few sessions at Mumbai. Very good place, lovely city, particularly the weather is very good. Shall we go ahead? Right. Here I'm wanting to teach you a small concept that is known as Hall effect. My dear friend, this is an experiment and it is used to, this experiment is performed in the lab. Actually, suppose it is a semiconductor and manufacturer has done doping. He put a label कि मैंने phosphorus से इसकी doping की है, इतना carrier है and all this, and it is sold to you. You take it from the market. Now due to any reason the label which was stick to it, जिस पर सारा description इसके बारे में लिखा था, that has been gone. Now just merely by observing this object, you cannot say whether it is N-type semiconductor or P-type semiconductor. And until you do not know whether it is N-type or P-type, you cannot comment about the properties, because properties of both of the types are totally different. In N-type, majority carriers are electrons, in P-type majority are holes. So in N-type conductivity would be according to the electron, P-type conductivity would be according to the hole. So we must know what is the type of the semiconductor. So to know this thing, although this will be told by the manufacturer, but suppose you bought it and due to some reason there is no any label stick on this. Now in lab, how can you find out whether it is N-type or P-type semiconductor? So Hall effect is answer for this. Hall effect tell us to determine the type of the semiconductor. इसकी मदद से हम सेमीकंडक्टर का टाइप पता कर सकते हैं कि whether it is N-type or P-type. Here I will be taking the help of a small concept of mathematics. And I may assume that ki all of you may be knowing a little bit vector, little bit things related with the vector. Still I will be revising it. अखिलेश गुप्ता पूछ रहे हैं कि सर टिल व्हाट टाइम यू रीड इन नाइट. बेटा ये अभी तो मेरा कोई स्टूडेंट लाइफ नहीं है, तो इट्स नॉट अ फिक्स्ड शेड्यूल, so you should not get inspired from my schedule. It is very random one, because now I am in job, so my schedule changes according to the requirement of company, according to the requirement of organization. हाँ, अगर कल की बात करें तो कल up to 2 o'clock I was sitting over there. I was trying to study, but normally I try to sleep by the 1 o'clock or 12 o'clock. मैं कोशिश करता हूँ कि सो जाने की कोशिश हो, ताकि एटलीस्ट 6 hours की नींद मिल जाए. तो 6 hours is 6 hours of sound sleep is required in order to function the brain and body efficiently. सो मैं स्लीप से कंप्रोमाइज़ नहीं करता हूँ, और इवन इन रिलैक्स शेड्यूल, व्हेन एवर आई गेट टाइम, व्हेन एवर आई गेट अपॉर्चुनिटी, देन आई स्लीप एंड आई ट्राई टू स्लीप एज मच एज आई कैन. Few days back, I took a sleep of roughly around 17 hours. 24 आवर की ड्यूरेशन में मैं 17 घंटे सोया था. तो व्हेन एवर आई गेट टाइम आई ट्राई टू टेक द साउंड स्लीप, बट इन रेगुलर शेड्यूल स्टिल आई ट्राई टू मैनेज 6 आवर्स ऑफ स्लीप. बाकी सब चीज़ें कटौती हो जाएंगी, लेकिन सोने से नहीं होती है. राइट, वेक्टर का कुछ कंसेप्ट हम यूज करेंगे. एक्स कैप, यू नो, यूनिट वेक्टर अलॉन्ग एक्स एक्सिस. Y cap is unit vector along y axis, and Z cap is unit vector along Z axis. So we have this kind of thing. X cap cross Y cap is equal to Z cap. Y cap cross Z cap is equal to X cap. And Z cap cross X cap is equal to y cap. अगर आप इसको चेंज कर दें, ऐसे कर दें, x cap cross z cap, so you may be knowing it is minus y cap. Let us suppose we are having two vectors a, and cross product of a and b is a b sin theta, where a and b are the magnitude of ab, sin theta is angle between them, and n cap is vector which is unit vector which will tell the direction, and that direction will be according to this, right? So first of all, you please note down this, then it would be easy for me to explain the Hall effect. One question has been asked from this Hall effect. No, that is Mukul Sachdev, that is different thing. ये हॉल नेम है व्यक्ति का, वो हॉल मार्क नहीं है. ये हॉल साइंटिस्ट है, उसका नाम है, और ये एक्सपेरिमेंट दूसरा है. वो हॉल मार्क तो प्योरिटी की गारंटी देता है. दैट्स अ डिफरेंट थिंग, टोटली डिफरेंट, नॉट रिलेटेड विद द हॉल मार्क इन द गोल्ड, राइट. अर्पित देव पांडे जी कह रहे हैं कि सर कहाँ उतनी दूर जा रहे हैं आप, लखनऊ बनारस घूमा जाए, आइए. अरे अभी तो हम पूरा भारत घूम के आए हैं, बनारस भी घूमे हुए हैं. अभी 2 महीने पहले मैं अपनी माता जी के साथ विभिन्न तीर्थ स्थानों की यात्रा पे था. तो बनारस एंड ऑल दिस, बनारस, जगन्नाथपुरी, गया, सो मेनी प्लेसेस, जो ये पूरा पार्ट पड़ता है वहाँ है. और लखनऊ तो अपना घर है. तो अभी जनवरी में लखनऊ, अभी मैं 12 तारीख को लखनऊ जा रहा हूँ, एक शादी अटेंड करना है. 12th को आई वुड बी, इनफैक्ट लखनऊ से भी आगे जा रहा हूँ, सुल्तानपुर, देयर इज़ अ सिटी रफली अराउंड 100 किलोमीटर अवे फ्रॉम लखनऊ. सो आई एम गोइंग ऑन 12th of December ओवर देयर. सो ये तो घर है. आलोक कह रहे हैं कि सर उत्तराखंड आइए बाबा केदारनाथ बद्रीनाथ के दर्शन करने. हाँ बेटा, उत्तराखंड तो खैर काफ़ी घूमता रहता हूँ. आप कहाँ हो, अपना नंबर भेजिएगा. उत्तराखंड तो मुझे लगता है साल में 2-3 बार तो ज़रूर जाता आता हूँगा, क्योंकि दिल्ली के करीब है, और जब भी फ्रस्ट्रेट होता हूँ, थकता हूँ, तो पहुँच जाता हूँ उत्तराखंड की वादियों में मज़ा लेने के लिए. आइए, लेट्स गो इट. ये हटाऊंगा मैं. आपने अगर इसे लिख लिया हो तो प्लीज टेल मी वेदर यू हैव रिटन आर नॉट, सो दैट आई कैन रिमूव इट. मनदीप सिंह इज सेइंग सर JNK आ जाओ इस विंटर में स्नोफॉल. मनदीप जी, JNK में कहाँ से हो आप? JNK लास्ट नवंबर में आई वाज देयर. मैं पटनी टॉप वगैरह गया हुआ था. पटनी टॉप में था, उसके आगे भी गया था. श्रीनगर से तकरीबन 30-40 किलोमीटर पहले एक आर्मी कैंट बेस है, वहाँ गया हुआ था. और JNK इज़ सो ब्यूटीफुल पार्ट ऑफ आवर कंट्री, बहुत ही खूबसूरत जगह है. लिख लिया आप लोगों ने? Shall we go ahead? Right, I am removing it. To do the experiment, we take a rectangular or square shape rectangular or square shape. To do the experiment, I take rectangular or square shape राइट इस तरह का स्पेसमेन पीस ले लेते हैं. नाउ यू सी like this. It is x axis, it is y axis, and it is z axis. Let us suppose the thickness of this specimen is t and width is w. The width is w and thickness is t. To perform this experiment, we apply a voltage such that a current flows in the x direction. We apply a voltage such that the current flows in the x direction and a magnetic field along z direction. I am making two specimens, one more identical kind. X, Y, Z. This is thickness T, this is width W. Again, I am assuming that we apply voltage such that current is flowing in x direction and magnetic field is along the z direction. We apply like this. I am assuming that this is p-type specimen. Let us develop theory for the known semiconductors and then once we know the theory, then unknown semiconductor को उसी तरह से arrangement करके and देख लेंगे किससे match कर रहा है and accordingly we would be having conclusion कि whether it is n type or p type. So let us suppose this is p type and this is n type. This we are assuming. ऐसा हम assume कर रहे हैं. ये कोई एक स्पेसमेन आप बनाओ, दूसरा वैसे ही रिपीट कर लेना. पहले एक बनाओ फटाफट. मनोज जी कह रहे हैं कि सारा इस समय सारा भारत आपके साथ लगा हुआ है. हाँ, ये खुशी की बात है कि सारा भारत इस समय मेरे क्लास में है. कम टू गुजरात वाइट डेजर्ट. यस यस, आई हैव बीन ओवर देयर. अ ब्यूटीफुल प्लेस, ब्यूटीफुल पीपल एंड गुजरात इज़ वेरी क्लोज टू माई हार्ट. My father was when I started to study, so family members were having huge financial crunches. So one of relatives said with my father, you can come with us to Gujarat. That is a place which will give you certain good employment. So my father went to Surat. There is a place in Gujarat, Surat, the diamond city. And he was a watchman in a diamond company. So when he was in Surat, I was at that time in 11th class. So I visited so many times Surat. I think in 11th class I visited, 12th I visited, and after that once I visited. But within 3 years he got severe paralysis attack. So he has to leave the city. But 3-4 times I have visited that beautiful city. I have some very friends, very good friends from my childhood in that city. Childhood I mean the teenage when I was in school. Have you drawn it? Shall we go ahead? Northeast, I have Jugunshi. Yes, very beautiful. One of the finest part of our country. And in 2019, I visited these Seven Sisters. I like it. And if you are from Nagaland, guide me. I will try to again visit. Nagaland, I was for very brief tenure at the Nagaland, but Assam, a good time and Meghalaya, I was there, and Arunachal I like too much. In Arunachal I was roughly around for 4-5 days, so roughly around 15 days I took to visit the northeast, and that is a very beautiful place. And if you go for other part out of the Seven Sisters, you come to Sikkim. So in Sikkim there is a university, the Sikkim Manipal University. So in that Sikkim Manipal University, I was there 2-3 times for taking various lectures. Very beautiful place. Let's talk about it. Physics कहती है कि when there is a charge in motion and if that charge is kept in a magnetic field, then a Lorentz force would be applied on that charge. You see, current is flowing through this material. It means what? Charge is in motion. Then only the current is flowing. And this material is kept into magnetic field. So these charges will experience a Lorentz force. So Lorentz force is given as Lorentz force. FL is equal to Q VD cross B. Q VD cross B, where Q is charge with sign. So if I talk about electrons, so you see my dear friend, if it is n-type semiconductor, so mainly we are talking about electron, forget about the holes. Current is flowing in this direction. It means electrons are moving in this direction. This would be the motion of direction of electron. So drift velocity of electron is Bd and minus x cap, because the current is going in plus x direction, so drift velocity is in minus x direction, and this b is b into z cap along positive z axis. This is b into z cap. आइए जरा देखते हैं. For electrons the Lorentz force would be, for electrons Lorentz force will be FL is Q is minus Q electron के लिए, electron has negative charge, and this BD is VD minus X cap cross B Z cap. My dear friend, this minus and this minus will become plus, so it will become Q plus Q, ये minus and minus, and BD cross B, that is BD B. Angle between these two vectors is 90 degree. So sine 90. You see that this angle is how much? 90 degree. And then what is left? X cap cross Z cap. X cap cross Z cap. X cap cross Z cap. What is the value of X cap cross Z cap? Sine 90 is 1. So it is Q VD and B minus Y cap. This is the value of Lorentz force. It means Lorentz force is working in downward direction on the electrons, because upward direction is what? Upward direction is y-axis, so minus y is downward direction. So Lorentz force is working, Lorentz force is working in downward direction, that is negative y direction on electrons, Lorentz force is working in downward direction, negative y direction on electrons. अब एक चीज देखिए, अगर इलेक्ट्रॉन्स पर ये निगेटिव वाई डायरेक्शन में अप्लाई हो रहा है, सो टॉप पर जितने भी इलेक्ट्रॉन्स हैं दे विल बी मूविंग टुवर्ड्स द डाउनवर्ड. So at the bottom plate lots of electrons will come into the picture. So since electrons are leaving the top plate, so at top plate you would be having positive charge. जहां से इलेक्ट्रॉन हटेंगे उस जगह पर क्या आ जाएगा, पॉजिटिव चार्ज. सो फ्रॉम टॉप टू बॉटम अक्रॉस द थिकनेस ऑफ मटेरियल a potential difference is developed and hence a voltage is induced. Because of this voltage there would be an electric field. This electric field will also apply a force on the electrons, but that force is in the opposite direction. Electric field electron पर opposite direction में force लगाती है और hole पर उसी direction में. Positive charge पर force is along the direction and negative charge पर force is opposite to the direction. So the force on the electron due to this field is upward. So this Lorentz force and this force under steady state will cancel each other. So when they cancel each other, these electrons will remain stable at this point. Because अगर net force zero हो जाएगा तो move नहीं कर पाएंगे. So initially they start moving due to FL. Then EH developed. EH applies force which cancel FL, and this way the net force becomes zero under steady state, and when the net force is zero, then these electrons will remain at bottom plate and at the top plate positive. So a voltage is induced which is plus at the top and minus at the bottom if it is n-type semiconductor. ठीक. Now if it is p-type semiconductor, so what would be the Lorentz force you see? For p-type semiconductor, FL is plus Q, right? You see, p-type means holes. So holes will be moving along the direction of current. So BD is equal to BD x cap. It is BD x cap. Right. Now you see, my dear friend, FL is Q and BD cross B. So BD x cap cross B z cap like this. ठीक, क्योंकि B तो अभी भी z डायरेक्शन में ही है. सो एंड प्लस Q चार्ज हमने लिखा क्योंकि होल्स पर किस तरह का चार्ज है, प्लस Q. सो इट वुड बी Q BD B sin 90 and in the bracket x cap cross z cap. So it comes out as FL, that is the Lorentz force will come out as Lorentz force FL will come out as Q BD B. Sin 90 is 1, that is minus y cap. This is minus y cap. It means force on holes is working in negative y direction, negative y direction, that is downward direction. Force on holes is working in negative y direction, that is downward direction. डाउनवर्ड डायरेक्शन में फोर्स काम कर रहा है. ठीक, आइए जरा बात करते हैं. दिस इज द फोर्स ऑन द होल्स. सो जितने भी टॉप पर होल्स होंगे दे वुड बी कमिंग टू द बॉटम साइड, सो दे विल गेट एक्युमुलेटेड ऑन द बॉटम प्लेट. So if holes positive charge are leaving, then at the top there would be negative charges. So this way a voltage is again developed in p-type semiconductor also, but the direction of voltage is reverse, minus plus, and this is the Hall voltage, right? My dear friend, now the field direction is this EH. पॉजिटिव चार्ज पर फील्ड अपनी डायरेक्शन में ही फोर्स लगाती है, तो FL को ये फोर्स अपोज कर देगा एंड अंडर स्टेडी स्टेट दे विल रिमेन स्टेबल. My point is, whether it is n-type or it is p-type, the Lorentz force is always working downward for this arrangement. In the n-type also it is working in downward direction, and in the p-type also it is working in downward direction. So now we will use this fact to find out type of semiconductor. Let us suppose this is unknown semiconductor. I give a current in x direction and put it into a magnetic field which is in z direction. Then I will measure voltage at the bottom plate. If the voltage at the bottom plate is positive, then I will conclude that at the bottom plate holes has accumulated, so it is a p-type semiconductor, right? But if we measure the voltage and at the bottom plate voltage is negative, then I will conclude that electrons has accumulated at the bottom plate and it is n-type semiconductor. So this fact what kind of voltage is produced at the bottom plate, that will tell you type of the semiconductor. If negative voltage, it is n-type. If positive voltage, it is p-type. So this fact we are using. Once we calculate this voltage, then we can use to calculate several other parameters. How? You see, मैं किसी एक के लिए explain कर देता हूँ. Under steady state net force should be equal to 0 because charges has become stable. So under steady state net force is equal to 0, equal to 0. So this is F net. F net is equal to Q BD cross B plus Q EH. EH is force due to Hall electric field, the developed field. This must be equal to 0. So no matter it is hole or it is electron, for both this will remain same. Q will get cancelled. If it is plus Q cancel, minus Q cancel. This side it comes to 0, and we are having EH is equal to minus BD cross B. To remove this minus sign, you can have B cross BD, right? B cross BD, अगर magnitude wise बात करें तो EH is equal to B BD sin 90, right? This would be the value. My dear friend, in the last lecture, I told you when I said conductor, so I told you NQ mu N into E. I also told you BD is equal to mu N into E. So it means J is equal to NQ BD. So it means BD is equal to J upon NQ. N is number of electrons per unit volume, Q हर एक पर charge. So NQ is charge per unit volume. So J upon rho B. Rho B is equal to NQ, and this is charge density. Charge density, that is charge per unit volume, coulomb per centimeter cube. This is charge density. So you can put this value. You will have B J upon rho B, right? Instead of BD, you can put this value. Now you see what is EH. EH is voltage per unit length. Voltage is developed across thickness. So it is BH by T. What is J? J is current per unit area. So current is flowing in this direction. Area is what? W into T. So I upon W into T. Let's put these two values. So if we put these two values, it will become VH by T, and this is B upon rho B I upon W into T. So यहाँ से T and T cancel out, and this comes out as VH is equal to 1 upon rho B B I upon W, right? So we can have RH into VI upon W. RH is this. Now you see, my dear friends, RH is 1 upon rho B, that is 1 upon NQ. This RH is known as Hall coefficient. RH is known as Hall coefficient. It is known as Hall coefficient. इसे हम लोग Hall coefficient कहते हैं, और VH को Hall voltage कहते हैं. VH बॉटम प्लेट पर मेजर करो, इसका साइन आपको बताएगा कि whether you have N type semiconductor or P type semiconductor. VH you can measure by voltmeter, and B you are applying, you know. I you are applying, you know. W is spacement width, you know. So you can calculate rho B. Rho b is what? N into Q. Q we know 1.6 into 10 raised power minus 19. So from this experiment we can calculate N. N is what? Electron concentration, means charge carrier concentration. So once charge carrier concentration is known, we can calculate conductivity, we can calculate mobility, we can calculate everything. So this way this experiment will help us to determine experimentally what is the type of semiconductor, what is the conductivity, what is the mobility, what is the charge carrier concentration. Every parameter regarding the semiconductor can be determined with the help of Hall effect. आपको ये पूरी मैथमेटिक्स करने की जरूरत नहीं है. You should know these two formulas, relations, कि how the Hall voltage is varying with B, I and W and RH. What is Hall coefficient, that you should know, and then how Hall effect is determining the type of semiconductor. Lorentz force is working always downward direction. So if bottom plate voltage is negative, it means electrons has moved, and if bottom plate is positive, it means holes has moved. So this way we can determine by the voltage at this bottom plate whether it is N type or P type semiconductor. चलिए लिखें. EH is voltage per unit length. EH is always from plus to minus. कभी भी electric field is always from plus to minus. किसी ने कहा कम टू उदयपुर. किस कॉलेज से पढ़ रहे हैं उदयपुर में आप? जिनेश जी, last year I was in Udaipur in Chittor, near about Udaipur in Chittor, Mewad University, and there I took a seminar. There were roughly around 500-600 students. It was a very wonderful interaction with the people, and people of Rajasthan are so lovely. They are very good host. Bangalore तो बहुत बार. Vandana is asking Bangalore. Yes, Bangalore I have been so many times. Is it done? Yes, Devanshu. Nalanda is very it has very historical significance. Nalanda has very historical significance. Geography is also very good. MP तो मेडी जी का सेंटर ही है. MP तो गजब है. MP has so many beautiful places. MP तो अभी 2-3 महीना पहले था भोपाल में. Done? प्लीज नोट डाउन. पहले N टाइप के लिए कर लीजिए, तो फिर मैं P वाला दिखा दूंगा. फर्स्ट टू डी. MP तो गजब है. Please do it quickly. Geetanjali College. Yes, Geetanjali also I took a seminar. Jodhpur, MBM Jodhpur, almost every year I used to go Ansu. And in Jodhpur I have so many students. Jodhpur has tradition to get IES. So from Jodhpur, so many of my students, Mahesh in electrical engineering, he is presently director and placed in Maharashtra, and Milan Krishna is placed in AIMS Jodhpur, and so many students. Rahul Naredi, IAS rank 3 is from the same college, MBM Jodhpur. And so many of my students are from that beautiful college, MBM Jodhpur, and that's Jodhpur is a very lovely place. Is it done? EH इलेक्ट्रॉन पर जो फोर्स लगेगा बेटा अपोजिट लगता है. Force is like this. Force is Q into EH. Q is what? With sign. So electron के लिए minus Q EH. So if EH is downward, force will become upward, right? And hole के लिए क्या हो जाएगा? Plus Q हो जाएगा. तो along the direction of field. Abhinav answered your query. Force is Q into EH. Good. MBM 2 very good. MBM बहुत अच्छा कॉलेज है, बहुत पुराना भी है, आई थिंक बहुत पुराना कॉलेज है. इस साल भी मेडीजी में MBM से यहाँ साकेत में भी बहुत सारे बच्चे हैं, जयपुर सेंटर पर भी बहुत सारे बच्चे हैं. सो देयर आर सो मेनी स्टूडेंट्स फ्रॉम MBM जोधपुर. एक्चुअली उस कॉलेज से ट्रेडिशन ही रहा है, बहुत लार्ज नंबर ऑफ स्टूडेंट्स मेडीजी में आते हैं. कॉलेज ने भी हम लोगों को हमेशा प्रेफरेंस दिया है, वो बीच बीच में बुलाते रहते हैं, कुछ ना कुछ प्रोग्राम करवाते रहते हैं, अवेयरनेस प्रोग्राम्स करवाते रहते हैं. आइए ये देख लीजिए. ग्रुप पर जुड़े रहिएगा आप लोग. जब छुट्टियों अभी जनवरी ऑनवर्ड्स मेडीजी की एक पूरी टीम है जो मेरे लिए सेमिनार्स वगैरह ऑर्गेनाइज करती है डिफरेंट कॉलेजेस में. तो अभी जनवरी से व्हेन आई विल बिकम फ्री आफ्टर कंप्लीटिंग सिलेबस ऑफ मटेरियल साइंस एंड ऑल दी सब्जेक्ट्स, सो फ्रॉम जनवरी टू मई आई यूज टू विजिट सेवरल कॉलेजेस ऑफ आवर कंट्री. सो मैं पुट करता रहूँगा, आपके शहर में आऊँगा तो मिलिएगा, ठीक है. बैठ करके चाय पर चर्चा करेंगे, मज़ा आएगा. चिंता मत करें, मैं आपके ऊपर चाय का बर्डन नहीं डालूंगा, चाय मैं पिला दूंगा. Shall we go ahead? Let's write. Yes, Giri, that I explained कि EH की डायरेक्शन सेम है, लेकिन फोर्स ऑन इलेक्ट्रॉन इज अपोजिट टू द डायरेक्शन ऑफ EH. So if EH is downward, force will be upward, right? Please इसका स्टेटमेंट लिख लें. समटाइम्स दे यूज टू आस्क स्टेटमेंट आल्सो. If a specimen ब्रैकेट में लिखेंगे मेटल और सेमीकंडक्टर is having current I in x direction and put into a transverse magnetic field B in Z direction, then an electric field EH is induced, which is perpendicular to both I and B. both I and B. If a specimen is having current I in X direction and put into a transverse magnetic field B in Z direction, then an electric field EH is induced which is perpendicular to both I and B. This is known as Hall effect. This is known as Hall effect. Hall effect. Hall effect is used to determine Hall effect is used to determine Hall effect is used to determine type of semiconductor. Type of semiconductor. Whether N type or P type. Second, चार्ज कैरियर कंसंट्रेशन, वोल्टेज मेजर करके N की वैल्यू, चार्ज कैरियर कंसंट्रेशन, मोबिलिटी, कंडक्टिविटी एटसेट्रा, इन पर्पजेस में यूज होता है. प्लीज नोट इट डाउन, जल्दी से लिख लें. बिल्कुल मनोज, मोस्ट वेलकम. बोकारो स्टील सिटी विजिट किए हैं? जी जी जी, बोकारो गया हूं, और लेकिन बहुत पहले, आई थिंक 2016 या 17 के आसपास गया हूं. इस बार अभी 2 महीने पहले बोकारो से हो के निकल गया था, मतलब वाज नॉट स्टेट देयर, बाय रोड कहीं जा रहा था, तो जस्ट बोकारो से हो लिया था. डन, प्लीज बताएं. आलोक, क्या श्रीनगर, एनआईटी श्रीनगर से आप पढ़े हुए हैं? गढ़वाल में आपके श्रीनगर में ही एनआईटी है, एनआईटी श्रीनगर. बिल्कुल, मुझे एक मैसेज करिएगा. वी आर एक्चुअली प्लानिंग अ सेशन विद एनआईटी श्रीनगर. एनआईटी श्रीनगर, मैं उत्तराखंड वाले एनआईटी की बात कर रहा हूँ. एनआईटी उत्तराखंड बेसिकली उसे कहते हैं. जरूर जरूर जरूर. शैल वी गो अहेड, आगे बढ़ा जाए. Noted? So this was about the Hall effect. Let us move to one more small theory, and then this is Fermi Dirac distribution. Fermi Dirac distribution function. Dear, it is mathematical function, distribution function. It is used to calculate electron concentration in the semiconductor. So from this mathematical function, sometimes they used to ask a few questions. Although it is a very big theory, I used to teach it roughly around 30-40 hours in total related with everything with this theory for the electronics student. जिन्होंने EDC पढ़ा होगा उनको पता होगा कि ये कितनी बड़ी चीज़ है यहाँ पर अगर इस क्लास में बैठे होंगे. बट हियर रफली अराउंड 10 to 5 minutes I would try to cover कि what this function is and how they can ask a question in general studies. All right. So electrons in solids, electrons in solids, वो solid metal भी हो सकता है, semiconductor भी हो सकता है, कुछ भी हो सकता है. In solids obey Fermi Dirac distribution function. Fermi Dirac distribution function. This is given as f of E is equal to 1 upon 1 plus e to the power e minus ef upon kt. One upon 1 plus e to the power e minus ef upon kt. This function is known as Fermi Dirac distribution function. Electrons follow this mathematical function. Here f of E, it is known as Fermi function. Fermi is the name of scientist who developed this mathematical function. This f of E, it gives probability of finding an electron at energy level E at temperature T Kelvin So EF will tell you the probability of finding electron at any temperature at particular energy level, right? Now you see, my dear friends, here K is Boltzmann constant, its value is always constant, so it is Boltzmann constant. T is temperature in Kelvin, right? EF is Fermi energy level, it is Fermi energy level. This is Fermi energy level, EF is Fermi energy level. So this equation is telling you about the probability of finding an electron. What is this Fermi energy level? It is an imaginary label actually, which will tell us below which electrons are available and above which electrons are not available. So basically it will be a kind of a line of control. So ये कोई actual energy level नहीं है. It is imaginary energy level. Fermi energy level is you see here. First of all, you see its mathematical definition. So then I would be explaining it. So Fermi energy level, Fermi energy level, that is EF, Fermi energy level. Please note down quickly. गुरदीप बाम, क्या नाम है, गुरदीप बम्बई। हाँ, बहुत बढ़िया लाइन इन्होंने लिखा है, दुनिया एक किताब है और जो यात्रा नहीं करते वो केवल एक पन्ना पढ़ रहे हैं, पढ़ कर रह जाते हैं। जी, मेरी सलाह होगी कि अभी पढ़ाई कर लीजिए खूब, एंड वंस यू गेट सेलेक्टेड एंड यू गेट अ जॉब, so there is in every job between the result and joining there is a time gap of 2 3 4 months. So in that 2 3 4 month निकल लीजिए भारत दर्शन पर, शुरू करिए उत्तर से और समाप्त करिए दक्षिण तक सब घूमते हुए। इस देश में ट्रेवल करना बहुत सस्ता है और बड़ा गजब का एक्सपीरियंस है। दिस ट्रेवल विल मेक यू अ वेरी गुड पर्सन एंड योर पर्सनालिटी विल गेट इम्प्रूव्ड सो मेनी फोल्ड। तो जरूर करिएगा। आइए, लेट अस डिफाइन फर्मी एनर्जी लेवल, कंसेप्ट ऑफ फर्मी एनर्जी लेवल। वी डिफाइन इट इन टू वेज। फर्स्ट वन इज एट T is equal to 0 Kelvin. 0 Kelvin is absolute zero temperature. So F of E is 1 upon 1 plus e to the power E minus EF, right, upon K into T, that is 0. Now if E minus EF is non-zero, so non-zero by 0 is infinity, but if you have to keep in mind, if E minus EF is negative, so negative by 0 is minus infinity, and E minus EF is positive, then positive by 0 is plus infinity. So let us suppose we have an imaginary energy level EF, right? So below this there are several energy states like this. Several energy states. For all these energy states, E is less than EF, then E minus EF is a negative value. If E minus EF is a negative value, then F of E is 1 upon 1 plus e to the power minus infinity. Negative by 0 is minus infinity. So negative by 0 is minus infinity, it means it is 0. So this comes out as 1 upon 1 plus 0, that is equal to 1. So it means all the energy states which are below EF, they have probability of finding electron 1. Probability of finding electron 1 means all these states are occupied by electron. All these states are occupied by electron. Occupied by electron. Right? Now you see, if E minus EF is greater than, E is greater than EF. Greater than EF means all these energy states. So for this, E is greater than EF. That is, E minus EF is equal to positive value. And if it is positive value, then what will happen, you see? So if this is for if E is less than EF, right? Now if E is greater than EF, if E is greater than EF, then you have F of E is equal to 1 upon 1 plus e to the power plus infinity, because non-zero by 0 plus infinity. So 1 upon 1 plus infinity, that is 1 upon infinity, is equal to 0. So it means all the energy states which are above EF, they have a 0 probability of finding electron, means all these are empty. So all these states are empty of electron. Empty of electron. So electrons are either below EF or electrons are found below EF. Above EF, this is empty. If I plot this function, let us suppose I am plotting, this is E and this is probability F of E. You know, the value of probability can be from 0 to 1, कोई भी value हो सकती है, and this is your EF. So according to this explanation, below EF we are having probability 1 and above EF this probability is 0. At EF the function is what? Discontinuous. Math का एक concept है कि point of discontinuity पर if you have to calculate value, take the average of these values. So average of these values will become 1 by 2. It means at EF the probability of finding is 0.5. 0.5 सिर्फ मैथमेटिकल है, एक्चुअली में EF पर कोई इलेक्ट्रॉन नहीं होगा, एक्चुअली इलेक्ट्रॉन्स आर बिलो इट एंड अबव तो एम्प्टी है. सो 0.5 मींस जस्ट अ रेफरेंस लिमिट, अ थ्योरेटिकल थिंग. EF पर कोई इलेक्ट्रॉन एक्चुअली में नहीं होगा, इलेक्ट्रॉन उसके बिलो होगा, लेकिन मैथमेटिकली मैं क्या कह रहा हूं कि यहां इलेक्ट्रॉन है यहां नहीं है, तो उन दोनों का एवरेज ले लीजिए तो इस जगह पर इलेक्ट्रॉन मिल जाएगा. सो आई कैन डिफाइन कि Fermi energy level is that energy level at which probability of finding electron is 0.5, या दूसरे शब्दों में Fermi energy level is that energy level below which all the energy states are occupied by the electron and above which all the energy states are empty of electrons. So you can write Fermi energy level, Fermi energy, yeah, at absolute zero temperature, at 0 Kelvin. 0 Kelvin is known as absolute zero temperature. At absolute zero temperature, Fermi level या EF is that energy level below which all the energy states are occupied by the electron. All the energy states are occupied by the electron, and above which all the energy states are empty of electron. EF is that energy level below which all the energy states are occupied by the electron and above which all the energy states are empty of electron. This is one way to define the Fermi energy level at 0 Kelvin. Please note it down. नहीं बेटा, कंडक्शन बैंड नहीं है, ये एक मैथमेटिकली एनर्जी लेवल बना रहे हैं. तो ऑब्वियसली इलेक्ट्रॉन अगर 0 केल्विन पर देखो तो कंडक्शन बैंड में तो कोई होता नहीं है. सो कंडक्शन बैंड अपर एनर्जी स्टेट्स हैं जो खाली हैं, जहां 0 प्रोबेबिलिटी है, और ये बिलो है, बैलेंस बैंड है जो भरा हुआ है. तो EF जो है वो कहीं बैंड गैप में कोई एनर्जी लेवल होगा, दैट इज इमेजिनरी एनर्जी लेवल, उस पर कोई इलेक्ट्रॉन तो पाया नहीं जाएगा। एक मैथमेटिकल कंसेप्ट है कि इसके नीचे पाया जाएगा, इसके ऊपर नहीं पाया जाएगा। ठीक, सो जस्ट इस डिफिनीशन से मतलब रखो और कुछ नहीं। आइए, सेकेंड वे ऑफ डिफाइनिंग इज एट T does not equal to 0 Kelvin. At T does not equal to 0 Kelvin, let us suppose we are at non-zero temperature. So F of E is equal to 1 upon 1 plus e to the power E minus EF upon KT. ठीक, KT नॉन जीरो है, तो अगर मैं E की वैल्यू EF पुट कर दूं, इफ E इज इक्वल टू EF, देन क्या हो जाएगा, F ऑफ EF इज इक्वल टू 1 अपॉन 1 प्लस E टू द पावर 0, सो इट विल बी इक्वल टू 1/2। इट मीन्स नॉन जीरो टेम्परेचर पर भी फर्मी एनर्जी लेवल वो एनर्जी लेवल है जिस पर इलेक्ट्रॉन के पाए जाने की प्रोबेबिलिटी 0.5 होगी। सो EF इज that energy level at which probability of finding an electron is 0.5 या 50%। डिफरेंट टाइप ऑफ सेमीकंडक्टर में फर्मी लेवल की पोजीशन बैंड गैप में कहां पाई जाएगी उससे रिलेटेड क्वेश्चन होता है। सो आई वुड बी शोइंग यू दोज पोजीशंस। प्लीज डू इट क्विकली। मैं ये डेराइव नहीं कर रहा हूं, आपको याद रखना पड़ेगा बिकॉज डेरिवेशन इज वेरी लेंदी, सो जस्ट मेमोराइज इट। फॉर एन इंट्रिंसिक सेमीकंडक्टर, फर्मी लेवल इज एट midway of conduction band and valence band. So it is in the band gap but in between the conduction band and valence band. So for intrinsic semiconductor EF lies in the mid gap of semiconductor. ठीक, for this is for intrinsic, it is for intrinsic। याद रखना पड़ेगा, इसका डेरिवेशन नहीं करा रहा हूं। जिनको डेरिवेशन में इंटरेस्ट हो, सो मेडी जी के यूट्यूब चैनल पर देर इज अ वीडियो ऑफ अप्रॉक्सीमेटली 4 आवर्स, मेरे नाम से पड़ा होगा, सर्च करके देख सकते हो। 4 घंटे का वीडियो जिसमें यही डेराइव कराया हूं, ये जो 3 चीजें लिखा रहा हूं। For n type, for material science you need to memorize this conclusion, that's it, need not to derive. For n type, Fermi level is closer to the conduction band but below it. EF is closer to conduction band but below it, and for p type semiconductor के लिए EC, EV, EF, ठीक, EF is closer to valence band but above it. ये p टाइप के लिए है, दिस इज फॉर p टाइप. ये तीनों बना करके याद कर लो, दैट सफिशिएंट. इसको डेराइव नहीं करा रहा हूं, बहुत लंबा टाइम लगता है, नॉट रिक्वायर्ड फॉर दिस केस. Someone asked when there was conductor and insulator, then why there is a need to develop semiconductor. The need was कि when you make conductor, when you make a computer with a conductor and insulator, so the size of a computer is such a small that you will need at least one truck to move it from one place to another place. But the beauty of semiconductor is that that size of computer has been reduced in such a small way that you can put it in your pocket and can move wherever you are wanting to go. So that's why we develop semiconductor. Is it done? Shall we go ahead? Yes, E is equal to EF is just an imaginary energy level. Someone said that ki E is equal to EF. मैं आपका क्वेश्चन अंकुश नहीं समझ पा रहा हूं. Just to practice question. No need of making again and again notes. One note is sufficient, whatever you have made. So just to practice question, that is sufficient. Let us move on to the next topic. Next is semiconductor devices. Semiconductor devices. I will be briefly discussing with few devices, and इसमें कुछ भी explain कर पाना संभव नहीं है because devices take lots of time to explain. Just I am giving few points, note those points, memorize those points, that would be sufficient for the examination. First device is semiconductor diode. Semiconductor diode या PN junction. This is the first device. Here actually what happens, we take an intrinsic semiconductor and half of this semiconductor is doped with acceptor and half is doped with donor. So first portion becomes p type and second becomes n type. Where they are meeting, this can be known as PN junction. That's why this device is known as PN junction. It has one terminal. At the positive side we know it as anode, and at the negative side we say it as cathode. So it has two electrodes, so that's why it is known as diode. So it is a two-terminal semiconductor device. Now the symbol of this device, electrical symbol, is given like this. This is symbol of diode, A and K. This is symbol of diode. Symbol of diode. Right. The beauty of this device is that when you bias like this, bias means you provide voltage to this, high at the P and low at the N, then a large amount of current will flow through it. It is known as forward bias diode. Forward bias diode. A large amount of current flows through it. A large amount of current flows. It works like an on switch. It works like an on switch. Like an on switch. Right? That's why large amount of current flows. If you make voltage and current a relationship, it would be something like this. I and V, voltage, the current will be something like this, exponentially increases with voltage, right? When we bias it like this, we change the supply P and N. So P side negative and N side positive. It is known as reverse bias diode. It is reverse bias diode. Reverse bias diode. In the reverse bias diode, no current flows through the device, negligible current flows through the device. So it works like a off switch. Negligible current flows through it. So it works like off switch. It works like off switch, right? So you can get like this, negligible current, right? But ऐसा नहीं है कि you can apply any amount of voltage. After certain large value of voltage, breakdown of the device will happen, and a large amount of current will flow in the reverse bias, which will break all the bonds and device will burn out. So it is known as breakdown. This is showing that the breakdown of the device has taken place. You need not to know much details, but you need to know few points. You can use this device as a switch. When you apply voltage like this, it is on switch. When you apply voltage like this, it is a off switch. So it is a two-terminal semiconductor device which can be used as an electronic switch. It is a two-terminal semiconductor device. Semiconductor device which can be used as a switch. Please इतना नोट कर लें. This is the first device, semiconductor diode. हम लोग E इक्वल टू EF ले करके, यानी EF पर पता करना चाह रहे हैं कि व्हाट इज द वैल्यू ऑफ फर्मी फंक्शन. सो उसमें एजम्पशन वाली क्या बात है, E तो वेरिएबल है, E की कोई भी वैल्यू पुट कर दो. सो हमने E की वैल्यू EF पुट कर दिया और उस पर कैलकुलेट किया. Please do it quickly. Next is bipolar junction transistor, popularly known as BJT. It is a two-junction, three-terminal semiconductor device which can be used to design an amplifier and as well as switch. ये दोनों काम कर सकती है, ठीक. Both types of carriers, that is electrons and holes contribute in current. That's why the name is bipolar. BJT is a current controlled device. इसमें क्या होता है? There are two types of BJTs. First one is NPN BJT and the second one is PNP BJT. In NPN BJT, we took two N layers and a P layer is sandwiched between them. So one terminal is this, another is this, another is this. There are two junctions. One PN junction is this J1 and another PN junction is J2. This terminal is known as emitter. It emits charge carrier. So in this case, it will emit electron because it is N type. It emits charge carrier. This terminal is collector. So it collects charge carriers. And this is known as base. It controls the flow of charge carrier, from emitter to collector, It collects charge carrier from emitter to collector, right? Next one is PNP. PNP में देखेंगे जरा. So here PNP J1 J2 ठीक, E B C सेम फंक्शन, बस अंतर क्या हो जाएगा कि इलेक्ट्रॉन की जगह होल हो जाएंगे, क्योंकि इमीटर को चार्ज कैरियर इमिट करना है. सो इट मस्ट हैव वेरी हाई डोपिंग. सो डोपिंग concentration of emitter is greater than doping concentration of base is greater than doping concentration of collector. Doping concentration of emitter is greater than doping concentration of base is greater than doping concentration of collector. So emitter is the most heavily doped part of this device, and then collector is largest in area, collector is largest in size, and base is thinnest in size, base is smallest या thinnest in size. इसका मतलब इमीटर इन दोनों के बीच में है. ये डिजाइन करते वक्त हम ध्यान रखते हैं फॉर द प्रॉपर ऑपरेशन. सो प्लीज नोट डाउन अबाउट बीजेटी क्विकली. प्लीज नोट डाउन। किसी ने लिखा है पिछला पूरा नहीं हुआ, जल्दी से एक पिक्चर खींच लीजिए इसकी, ठीक है, नहीं पूरा हो पाया तो बाद में कर लीजिएगा। टेक द पिक्चर ऑफ दिस, इसकी पिक्चर लें, then this, then this, there are two p layer, उनके बीच में एक n layer है, that's pnp, just like npn. This will be emitter, this will be base, this will be collector. This emitter will emit holes, here the emitter will be emitting electrons, that's it. npn BJT would be preferred over pnp because electrons are preferred over holes, that's it. ठीक, जितना लिखा है इतना ही जरूरी है, इतना ही ध्यान रखो बस फॉर मटेरियल साइंस। शैल वी गो अहेड, आगे बढ़े। आइए, नेक्स्ट डिवाइस इज MOSFET. MOSFET is metal oxide semiconductor field effect transistor, that is MOSFET. Metal oxide semiconductor field effect transistor. It is a unipolar device, that is majority charge carrier device, majority charge carrier device, majority charge carrier device. ठीक, it is a unipolar device, that is majority charge carrier device. It consumes less power than BJT. It can also be used, it is used to design amplifier and switch. जो काम ट्रांजिस्टर करता है सेम ये भी करता है, द ओनली डिफरेंस इज कि इट कंज्यूम्स लेस पावर. इट इज वोल्टेज कंट्रोल्ड डिवाइस, इट इज वोल्टेज कंट्रोल्ड डिवाइस, वोल्टेज कंट्रोल्ड डिवाइस. दैट्स इट, बस इतना ही डिवाइसेस के बारे में. सेमीकंडक्टर इज ओवर, राइट. आज की क्लास भी यहीं पर खत्म करेंगे. Tomorrow we will be studying the last part of this chapter, that is insulator. Very small, insulator is up 1.5 hour or 2 hour at max topic. So tomorrow I will start insulator as well as magnetic properties both. Insulator will be covered in 2 hours and the remaining 1.5 hour we would be studying magnetic properties of materials. Tomorrow class timing is from 8:30 onwards. Tomorrow the class timing is 8:30 a.m. onwards, 8:30 a.m. onwards. Basically it is from 8:30 to 12. This is the class timing for tomorrow. Let's meet tomorrow. आज के लिए बस इतना ही. ठीक, जिन्होंने ना लिखा हो डिवाइसेस में पिक्चर ले लें. This, then this, and then this. Thank you. Have a wonderful day.